Okay, so let's continue. So as most of you think, this is like one day before the Chinese New Year. So I just want to make this video so like, you can study at your own pace. Okay. So essentially, we want to say something about the expansion works. Last time we were here. So expansion works is very simple. It's basically the volume of the system increase, which leads to the size of the expansions which do the works to the externals. So in this case, actually, we have to emphasize this. The work is done to the environment or to the surroundings. So we're always using the external pressures. So here, this is a derivative forms. So, okay, delta W is equals to minus F, okay, dz, and F is where the force like against the external force. Okay, because it's external force, so it needs to be related to the external pressure. Okay, to obtain the works, so it's going to be the interrogations of the work is equals to the integral from the initial volume to the final volume, which is P external. Okay. So this would make the case of expansions into two very simple cases. The first case is we always use is called free expansion. So free expansion is the external pressure is equal to 0. So when there is no external pressures, so it cannot do work to no external force. So that would lead to the delta W is equal to 0, so the work is always equals to 0. Okay, and for the case B, if we are actually doing works to externals, and this external is constant pressure, for example, the atmosphere pressures, so those atmosphere pressures would be constant no matter how hard you actually like doing expansion. You can have a very, very high pressure inside, but outside it's the same. So one of the example is a rocket engine, right? So rocket engine is a rocket is very high pressure inside, as high as could be 300 or something like that, 300 atmospheres. But outside is always one atmosphere. So or if you go to the space, it's going to be the 0 atmospheres, 0 pressures. So it goes transmission from the constant pressures to free expansion. Okay, so obviously, these two cases, this is 0 and this is constant, they're actually getting a very different work because one is 0, one is having the work. So another case is the reversible expansion, because we said in the free expansion as well as in the constant external pressure expansion, the pressure inside and outside is different. Right? So inside is always high, and outside is always low, and they're always different. But in this case, reversible expansions is a change that reverse as a very small, okay, infinitely small modification of the variables, right? So imagine if we have a system that will have a constant pressure inside, so of this gas, and while the system starts to expand, if the temperature doesn't change, the internal pressures is going to drop. So that means if you want to make this expansion reversibles, so the external pressure and internal pressure needs to be like equal with each other. So external pressure also needs to be changed. So in this case, right? So you actually think about like you remove one of the sands, like one grain of sand out of this pistons, and one of the time. So each time the pistons is only move slightly, okay, move very, very slightly. So one of the case, as I said, is called like a temperature constant. So we said this is isothermal reversible expansion. Okay, isothermal reversible expansion is delta W is equal to minus P external dV. So this is always hold. Okay, always correct. And the W is equals to minus the VI over VF, right? So that is dP. So according to the perfect gas law, so we know what is the P related to the volume. So that would be the minus the nRT over V dV. So this is the interrogation. We got the minus nRT log VF over VI. Okay. So and that's essentially, we have the P and V diagram. In this diagrams, the work would be the area of this curve really swing off, right? So what kind of area they actually swing off. And again, this pressure is the external pressure. So essentially, the interrogation means we are actually getting infinitely more steps to getting the work down. Okay. Yeah. So this thing is very simple. So obviously, this works. Okay. This area is going to be bigger compared with the free expansion, because free expansion doesn't do work, as well as a constant pressure expansion, because constant pressure expansions means the final pressure is equal to the external pressure. So you only get this much, okay, the size, right? So the maximum work can do for the expansions. So we see we have a final stage of the system. The final stage is where there's a temperature of the system. You have a final pressure of the system, as well as a final volume of the system. So these three define the state of the systems. Okay, within these like three different process, I mean, so free expansions, constant pressure, and isothermal. Okay, their final state of the system is the same, but you can see the work can be very different. So which means the work is a past function. It is not a state function. Okay, that is simple. Okay, so let's do a quick in-class exercise. Well, like you need to do it at home. So again, like this time, so our in-class exercise is going to be counted towards the final marks, but because this is within the add drop period, so this exercise is not going to be counted. Okay, but like go ahead and do it. So when we actually really start the in-class exercise after the add drop period, it's going to be counted. Just like in case someone is actually after the add drop period, and it's going to be giving them disadvantage. Okay, so this is a class is already like an exercise is already open on the Moodles. Just go ahead and do it. Okay, calculate the work done when 50 grams of iron reacted with a hydrochloric acid, okay, in a closed vessels of a fixed volume, okay, or in an open beaker at 25 degrees Celsius. Okay, so I will give you, let's say, like 3 minutes. Okay, so you can pause the videos and just do this like on Moodles. Okay, so let's check our answers. Okay, so this is the answers. So the volume of the first one is, because it's a closed vessel, so it doesn't really expand. So the gas, the size of the system is the same, and then the volume, the work is going to be equal to 0. The second one, because the gas is generated, so they're actually going to expand out of the systems. So this system volume is actually increasing. The outside pressure, obviously, is the 1 atmospheres, so it's not going to change. So we were having the work is equal to P external delta V, and the V is how much gas was generated within this chemical reaction, because it's 50 grams of iron. So we know how much iron or how much hydrogen was produced in this case, because this is a chemical reactions. Iron plus 2 hydrochloric acid, and you're getting the iron 2 chloride and hydrogen. Right. So this is a calculation. So 50 grams is divided by the molar mass. It's this much moles of irons, and this much moles of irons would generate this much of moles of hydrogen. And then we have the work is equals to minus P external delta V. And because the TP is actually the, or the V is nRT over P, right? So it's actually going to be only related with the nRT. It's not even related with the external pressure. Okay, so this is something like it's something like interesting. Okay, if you think carefully. Okay, somehow like the work done in this case, the expansion work done in this case, is not going to be related with external pressure. It's only related with the temperature. Okay, so this later on translated into the entropy. Okay, entropy. Right. So if you think about like this, pressure goes lower and lower, eventually goes to be 0. Okay, how much? Well, really, the pressures, the work you're actually done. So like it's going to be the same. It's only related with the temperature. Okay. Okay, so let's take a look at this even simpler ones. Okay, so the in-class exercise 2. So again, so this is on Moodle already. So just go ahead and go there and do it. So a sample consists of 2 mole of helium is expanded isothermally, okay, at 22 degrees Celsius from this volume to this volume against the constant external pressures equals to the final pressure. B is freely against the free external pressures. Calculate the work for this. Okay, so like 1 minute, I think you will be able to finish this. Okay, you can pause the videos, finish that. All right, so again, so this is extremely simple. Again, so the work in this case, okay, it's sample vessels. Okay, is actually expand a bit, right? So they actually expand. Constant external pressure equals to the final. We know the external is whatever this the numbers is the delta V, right? So the P of the final, we need to calculate it what it is, right? So after the calculation of the P, you can calculate the work. Very simple. Okay, it's equal to these numbers. Okay, the B obviously because it's against the nothing, so against the vacuum, so it's equal to 0. Okay. So this is for the perfect gas. Okay, perfect gas is very simple because PV is equal to nRT. But in most case, okay, the gas is not really perfect. Okay, so like it's PV is not equals to nRT. Okay, so in real gas, so there are something else. For example, if we suppose there is an attraction force between the gas molecules in the system. Okay, because for perfect gas there is no attraction between them. Because there is attraction force, those attraction force would generate some kind of internal pressure. So some kind of pressure-like interaction when the 2 gas molecules getting closer to each other, so they are harder to be like separated. So this force would generate some or will subtract some kind of force, some pressures inside the systems. So this is divided into here. This is A over V squares and N squared. Okay, N is a number density, or N is the number of the molecules essentially, right? So A is a constant. Okay, so we can derive expressions for the reversible isothermal expansion gas. Okay, and so like if like just consider like whether this work is more, okay, or work done or less the work done to the surrounding when they actually expand. Okay, compare with the perfect gas. Okay, so again, like you just try again with this. Okay, so this is how it is. Okay. Work is equals to minus VI to VF and the P dV, because this is a reversible expansion. So that means the P external, that means the P external is equals to the P internal. So we can use this P here to replace the previous like the perfect gas equation. So nRT minus N squared A and V squared, right? So these, we're going to get these numbers. Okay, interrogation, this part is our perfect gas term, and this part is additional term, right? So this is going to give us the minus nRT log VF over VI. So this numbers, okay, this numbers because this log is going to be greater than 0 and there is negative. So overall, the work is negative. That means the work is down to the surroundings when they actually expand. So in this case, okay, you have the n squared a over Vf. Okay, divide this. So this minus n squared a 1 over Vf minus 1 over Vi. Right? So if this is a expansion, so that means, okay, Vf is going to be greater than Vi. So this number is negative. So this is negative. When this is negative and there is a negative, so it becomes positive. So it becomes less negative. Right? So overall, it's less negative. So that means the work is down to the surroundings, to the environment. It's smaller compared with the work down to with the perfect gas. So this also makes sense, right? So because while they actually expand, the gas expands, some of the energies was stored like between the interaction of the molecules, right? So this is making sense. Okay. So this is one of the corrections, okay, which needs to be considered for perfect gas when you're actually thinking about the real gas. And there is another thing is what is the size of the molecules. So this is like these two terms add together is a van der Waals gas. Okay, so we can talk about that later. All right, so that is all about the heat, the work. And next we want to talk about the heat. So as I said, like heat and work, there is just like two ways of how the energies can be transferred from between the system and the surroundings. Okay, there is just work and heat according to the thermodynamics, first law of thermodynamics. So the delta U is equal to Q plus W, right? So this is just the two terms, two possibilities. Heat is compared with the work is a transfer of thermal energies, so which is stored in random motion of the molecules, right? So think about like this is where the heat is releasing, okay, from like peoples, and also this represented the radiation comes off from the heat, right? So it's starting with the low temperatures to the high temperatures. So at this moment we know that, okay, nowadays we know this temperature is because of the random motion of the molecules inside the systems. So when they actually, the motion is slow, it's a low temperature. When they actually move faster or more vigorous, so this is a high temperature. So temperature between the systems and the surrounding leads to the transfer of the thermal energies. Essentially, if you have a glass rod here, and this is a hand, you put it on it, so the heat, okay, is going to basically get the molecules or atoms vibrate more faster inside the glass rod, and this glass rod is going to like transfer these vibrations to your hands, like according to this heat transfer. Okay, and some of the materials actually conduct the heat better. Some of the materials conduct the heat like not as good. For example, this is a glass rod, so this heat conduction is really poor. And compare with metals, so if you have a piece of copper, so the heat conduction is much higher. Okay, so we can talk about like what's going on inside like later on. Okay, so it's either ways. So heat flow is always from the high to low temperatures, so we never see it's going backwards, which is like during the attainment of the thermal equilibrium. Right, so it's flowing in one direction. So there are two possible processes involved the heat transfer. So the first one is the heat flow from the solutions, from the system to the external. So this is called the exothermic process. If the heat is going inside the system, it's endothermic process. So release energies as a heat to the surroundings, compare with the acquire of energies as a heat. Okay. There are like if this is an endothermic process, okay, there's something going on. Let's say, okay, they're burning combustion engines or whatever, burning some fuels, And if the system is somehow isolated from the solutions, from the surroundings, and the heat really just cannot be released to the environment, so which will cause the temperature of the system goes up. Okay, this is called adiabatic heating. Okay, and if this is isothermal, it's a diathermic reaction, like process, so isothermal. So comparatively, this is also like applied to the endothermic process. Okay, for the exothermic, we're gonna basically like if we have a fire, right? So the fire means the heat is going out, and if you have ice melting, this heat is going in. So when the heat goes out, again, when it comes out, it's a negative sign. Okay? And this one is a positive sign. Okay, this is what kind of process will lead to the internal energy goes up. Okay, increase is we call it the positive sign. Okay, if it goes down, it's negative sign, because here this energy is released. Okay. So there are several important processes we always mention about, like during the course. So that is isothermal, isobaric, isochloric, and adiabatic. Okay, so it just refers to the temperature, pressure, and volume, or the heat flow. Okay, whether all of these can be kept, or one of these can be kept constant. Okay, and this is adiabatic. Yes, we're going to mention this repeatedly. This is more difficult compared with others. Okay, diathermic is permits heat to flow through the boundaries, and the heat system is the same. Okay. So, so in here we said the heat and the work is a path function, because it's depending on the system process. It's not only depending on the final state of the system. So mathematically, we will say this is a state function versus a path function. So if a physical property is that depending only on the final and the initial state, so this, and independent of how system reach that state, it's called the state function. And state function have certain properties, like when we actually like first time talk about the mathematical derivations, like the second derivative, or all of these properties is only applied to the state function, not applied to the path function. Okay, so one example is for the state functions versus path functions. Okay, state function is let's say how much energies or potential energies for these people, okay, goes from here to here, right? So it's only depending on where this people is. It can be here. So like, okay, the total energies is mgh, right? So the mass gravitational force by the height of that. But how much path or how much length they actually walk on is depending on this, like taking this route versus this route, and maybe like how much work these people done is also going to be depending on the path, right? So this one is taking longer versus this one is taking shorter. Okay, so that is the definitions for paths and state functions. Okay, so in this case, like if we have a process like this, so 3 mole of hydrogen gas in 1 bar, okay, this temperatures goes into a 3 mole of hydrogen. So like there's no chemical reaction, still the hydrogen gas, but the pressure goes higher, and the temperature is also higher. So we can draw this kind of graph like this. So starting from this point, okay, the temperature and the pressure goes to this point, okay, higher temperatures, higher pressures. If it goes from here versus goes from here, so this is the 2 possible paths, okay, possible A and B. So the work done through this path versus through this path is going to be different. State function is independent, like energy, mass, pressure. Path function is dependent, like the heat goes up and the work goes up. Okay, so one thing like we want to like know is because the work and heat is both path function, so that means they both depending on which path were actually taken. However, the energies, internal energies, is a state function. So that means the total delta U is actually constant. So that means that delta U is a constant from here to here, while the Q and the W is not. But Q plus W is equals to delta U is a constant. Okay? So that means like, okay, so if for a given process, okay, like they have the same initial and final state, and if you have a more heat generated, okay, or released, so it's going to be compensated by the work come from this process, right? So their add togethers is going to be constant, is conserved. Okay, so how to study the heat transfer in a certain process? Because heat is, well, ideally, like we can use some kind of measurement to measure the heat, but like measuring heat is much harder compared with the measuring of work, right? So like then like we're going to use this first law of thermodynamics to do that. Okay, and according to the first law, okay, delta U is equal to W plus Q. So if we know this one, so and know this one, and we know what is this. Okay, and if we really want to make some measurement, okay, for isochloric process, that means the volume is constant, so there is no extra work, no expansion works, so no extra. So we have a du is equal to delta W plus delta Q, and we can split these two, expansion work into extra work. And if this is like, because this is isochloric, so that means this is 0. And when there is no extra work, so if there is no extra work, so this one is also equal to 0. So that means that du is equal to dq, okay, delta Q. Okay, so in this case, we're saying du is equal to delta QV. V means this is constant. Okay, this is constant. So like, if the system does not do extra work, the isochloric thermal effect, which is QV, is equal to the change of internal energy. So this is actually makes sense much easier, because if we want to measure how much heat is flown in, we can just measure what is the internal energy change. For certain things, like if we know, okay, because there is certain process, right? So if the volume is constant, and we're just measuring what is the temperature of the system, and the temperature would be related with the internal energy. Okay, so this is a measurement. Okay, this is a measurement. Okay, it's called the calorimetry, which is invented by the French scientist Artin Lavoisier. So like who like discovered the oxygen. So it's very simple. So it's essentially some kind of a system like isolated, like from the surrounding. So like do not let the heat flow in and out of the system. Okay, so like a styrofoam cup would serve it, right? Okay, so in this case, there is a gas stirring, so you're just stirring out the inside and putting a thermometer and putting some water in there. Okay, so you're just measuring how much temperatures inside this cups, and then you know the heat. Okay, and in this case, because it's not sealed, so this is constant pressure conditions. So we measure the heat under constant pressure conditions. So this is a very simple constant pressure calorimetries, and we have could do the bomb calorimeters for measuring it. So in this case, everything is sealed. Okay, it's sealed from outside, so the total volume of the system would not change because it's sealed, and even you have a gas actually generated in here. Okay, so internally it's like this. You have a thermometer goes in. There are some waters. And you have some kind of reaction chambers. You could put something in and do chemical reactions. In this case, just showing is the combustion. So you have a sample cup, and inside here, if we want to measure how much heat was generated in the combustions, so it's filled with oxygen, and put something in, and you ignite it with whatever this this material is. You generate some heat, and this heat is going into this water, a tank of water, and then this tank of water increase in temperature, so you know how much temperature increase, and then you know it. Okay, there's a stirring bars to actually getting them more isothermal, this reach the equilibrium. Okay, and this is a real calorimeters. It's like this. So this is, you can see there's O-rings, and put it in, and you can put your stuff inside here. Okay, it's called the bomb calorimeters because it looks like a bomb, right? So it looks like a bomb, and you just put a little bit things inside, and they generate heat from there. So calorimeters is a study the heat effect, okay, of a physical or chemical process. So in this case, we know the Q is equals to something, right? So you want to measure in the Q, because in here this is a solid and as well as water, right? So there is water here, there's a solid, whatever this whole thing, and there's isolation outside. If we ignore the isolation outside, here this is just a chunk of material. And how much temperature rise is going to be proportional to the heat actually goes in or out of the system. And the constant, the ratio, is called heat capacity, right? So the Q, this is by definition. So there is two kind of heat capacities. The first kind of heat capacity is when the volume is constant. So this is called the CV. So when we actually have a subscription, this means this is constant, similar here, right? So we have a V and P. So heat capacities of constant pressures, okay, is called CP. So you have a CV is equals to, okay, this is actually like a partial U, partial T, and V is constant, and the CP is partial H, the entropy is divided by over the T as a constant pressure. Okay, so usually the CV and CP is constant over a short period of time. Okay, so they're actually very constant over here. And but if you look at for a large like the temperature range, they can varies. Okay, they can varies and can be expressed in this terms: A plus BT plus C over T squares. Okay, so this is for a small temperature range, it can be regarded as constant. So actually, this CV is or CP is very important thermodynamic properties of a material. Okay, so some materials would have higher heat capacity. Some material will have a low heat capacities. So why they have a high heat capacities? Okay, so if you think on the mechanisms or physical meanings of the heat capacities, so it really means, okay, how good a system can store thermal energies, can store energies before the temperature can rise. So if you have a more ways or more, like this system is just like there is more ways of storing energies inside the system, so they can store more before the temperature starts to rise, right? So for example, last time we were saying the gas, perfect gas, right? So gas, the monoatomic gas, they can move, okay, in X and Y and Z direction. So that's what corresponding to the heat capacities of storing within the translational mode of the motions in X and Y and Z direction. So each of the direction is stored half of the KT of the energies. So that would translate it into the heat capacity of the half of the R. R is the perfect gas constant. If you have more of the way of motions, for example, rotations, vibrations, so those things is going to be able to store energies into those motion states. Those motion states would causing the heat capacities higher. Okay, so can resistance to the temperature change. Like one example would be the water, right? So water have the hydrogen bond. Those hydrogen bond is one way of the vibrational energies. These vibrational energies would allows, okay, the energy stored there and very drastically, and they basically cannot raise temperatures as effectively if you're putting a little bit heat to it, right? Sometimes this is beneficial, sometimes this is not beneficial. Okay, so if you want to have a system that really, okay, can store energies as a term of thermal energies, you want this system to have a very high heat capacity. If you really wants to rise the temperatures effectively, then you want to have a low heat capacity. Right? So this is a little bit ancient or very old-fashioned way of doing the thermal measurement, and this is measuring the combustion heat of chemical reactions. Okay, so combustion means that a lot of heat can be generated, and there are more modern things actually doing it. Okay, modern ways, because some of the chemical reactions doing little heat was generated. Okay, or your sample size is too small, so you want to have this new equipment. It's isothermal titration calorimetries. Okay, essentially this experiment is like this. All right, so you have a cells, okay, and you have a sampling cells, and have a syringe, and this syringe is dripping the waters, okay, or into the cells. In the cells, there are some solutions, and this solution could do chemical reaction. The solution maybe can do the dilution. For example, you have some polymers or some kind of salt in there, and you add 1 drop of water there. So this is going to generate heat, right? So in this case, this is actually corresponding to the to the heat was generated, because actually how the system doing is you have a reference cells, you have a your sampling cells. Instead of measuring how much heat really or the temperature rise, so what this system do is they have a electrical coil here. So once this thing comes in, the temperature is going to be different between this reference cells and the sampling cell. So then the reference cell is going to add some heat by an electrical wire, and to compensate the temperature difference to make them equal. And if we make them equal, you know the heat is equal to how much electrical work was put in. So this is the data, it's 1 drop of the liquid in there, and you're getting more of these. Okay, and these is over time you have this, right? So for example, people can do is you have some kind of solution of the enzyme and have some small molecules, and because the small molecules or drugs actually bond with enzyme, so doing the inhibitations of enzymatic chemical reactions inside the body, right? So this would allows the bonding force between the small molecules and enzyme being measured. So this is basically the golden standard of doing this measurement. Okay, and actually, in our research, we do the same thing. So this is one of the paper we recently published. I think it's last year or something. So or 2 years ago. So what we have is we have a polymers and we have waters. So we're doing the titrations, and some polymers is going to give me the positive signal. Some polymers give me the negative signal. So this is one polymer, the second polymers, and we have the delta H, okay, in here, because this is a constant pressure systems. Okay, and we can get what is the delta H and entropy of the systems, like a dilution. And the implication is this polymers is when they actually combine or mix with the water, so they release heat, while this one they actually absorb heat. So this would makes the process very different, because actually one of my research is doing the active swimmers or nanorobots. So this is like a small particles with the size of a few micrometers. As you can see, they actually move, in this case, move forward, okay, under the heat, while this one is actually moving backwards, okay, and this is coded, it's moving forward, and this is moving faster, those kind of things, right? So this is because when the heat is a thermal gradient is applied, some of them is going to be releasing heat, some is actually absorbing heat, okay. Okay. So heat capacities, as I said, is really a means of how internal energies is stored there. Okay, there are several ways of storing energies in the motion of the molecules. There could be translational motion, there could be rotational motion, and there could be vibrational motion. Okay. And last time we were saying that for the monoatomic gas, okay, for this one, it only have one way of motion, so that is a translation. So they have X and Y and Z direction motions. Okay, so for the monoatomic gas on the constant volume, the energy flow into the gas is used to increase the translational motion of the gas. Okay, so that is this. So we can know, okay, what is this CV of the perfect monoatomic gas? So that is a partial U over partial T, as V is constant. This is by definition, right? So by definition. And because this is by definitions, like we can do it because putting another M. M means a per mole. Okay, so in our course, like we're always taking this. So V, okay, this subscription V or P means this is constant. When we put an M, means this is a per mole. Okay, so this is a heat capacity at constant volume. This is a molar heat capacity at constant volume, and we know the molar heat capacity at constant volume is U0 at the the internal energies at the 0 Kelvin, and plus the 3/2 RT divided by derivative over T is equals to the half 1.5 of the radial gas, perfect gas, constant. So this is a monoatomic gas. Okay, it's like this. Okay, CV, and for CP, because we were saying they're actually doing some external, doing some thermal expansion. Those for perfect gas is always equals to the RT. The work is always equal to RT. So the R becomes another R in here. So this is 1.5 of R, and this one is a 2.5 of R. So this is going to give the CV for monoatomic gas is a 12.47 joules per mole per Kelvin, and this is 20.8. Okay, so monoatomic gas. So there's a helium, neon, and argon. So you can see this is matched extremely well with the expectation. Yeah. And again, like this is a denotation for molar. Okay, so this is for the internal energies. Okay, for internal energies. And we just continue like with the enthalpies. Okay, enthalpies. So enthalpies is where is the energy transfer as a heat as a constant pressure. Okay, so so most chemical reactions or most processes is not done when the volume is constant, but it actually is open systems, so the volume can change. So that would lead to some kind of expansion works. Those expansion works, okay, would add additional terms in our equation. So we want to use that equations more conveniently. So we define this enthalpies. Okay. So it's in this case, the change of the internal energies is not equal to the energy transfer of the heat when system is free to change the volume because there is some extra work. So the energies, okay, the internal energy change is less than the Q. So in this case, okay, so it's basically just shown here. So by definitions, we know the enthalpies, okay, is actually energy transfer of heat at constant pressures. So we define the enthalpies is equal to U plus PV. Okay, so this is definitions. So as the derivative form, we have a dH is equal to du plus dPV. Okay, dPV. Here we're using d because, right? So this is exact differentials. Okay, and everything is the state functions. And we can put here, so the dH is equal to du plus, like this is one is to the v, another is to the p. So pdv plus vdp. And this part, okay, this part, du, we know, according to the first law of thermodynamics, is equals to the q plus w, right? Delta q plus delta w, and equal to this. And if we have a system that is at constant pressure, right? So external pressure is constant. So then we have the work or the expansion works. So that is equal to the negative of the P external dV. And we know the pressure of the system is not changing. So that means the dP is not changing. So the system pressure is external are the same. Usually, that's most of the chemical reactions or process. So we know this one is 0. And we know the external pressure and internal pressure, if they're actually the same, so these are actually cancel each other. So in this case, we have the dH is equals to RQ. Again, so this is at the conditions when the system pressure is equals to external pressure. So we have an external constant pressure. Right, so this is just like the stuff we wants to get. So dH is equal to delta Q P. So we said this is constant pressure one. So this is the delta H is equal to the PQ, QP. So QP we can define another one is a constant pressure heat capacities. Okay, over here. So as a summaries, we have a delta H is equal to QV is equal to CV delta T. We have a delta H is equal to QP is equal to CP delta T. Okay. So these things, although very, very simple, okay, I want everyone to go over this, think about this, okay, one more times, okay, in here, and really embed this in your mind that delta U equals to QV at the conditions when the volume is a constant and there is no extra work. And we have a delta H is equal to QP, means, okay, the delta H is equal to the heat at constant pressure and there is no extra work. Okay, because a lot of time in the exams, like I will see a student just using this. Okay, delta H is equal to Q, or delta U is equal to Q, no matter what. Okay, so that is wrong, right? So this is wrong. Like it comes with a conditions. With a conditions. There is no extra works, and there is either constant volume or constant pressure. All right. And for examples, like I could make ask you a question here. So for a combustion, okay, for a combustions. So I have the I have the, let's say in the rocket, right? So in the rocket, they have internal pressures. Okay, it's equals to some things, and they actually expand outside, have an exhaust gas, right? So over there, is this one hold? Is this one hold? Right. So in the combustion chambers, there's something really generate heat, right? So this heat does it actually comes out. Okay, you can think about that. All right, so for perfect gas, okay, for perfect gas, H is equal to U plus PV, so that is equals to this one. Okay, so this delta H is equal to here, and because the delta PV is equal to nRT, so we have a delta U is equal to delta of the nRT. Okay, so because we know for perfect gas, U is only a function of temperature, right? So it's not a function of anything else, and H is only a function of temperature as well. So it's not depending on the P and V, right? So this is only hold for perfect gas because there is no other force or interactions between molecules, right? So we can write it in this forms. H is equal to HT. So this is only a function of T. So for perfect gas, like the Cp and Cv is correlated because the Cv is equal to partial U plus partial T over P over T, and it's only a function of T. So this V doesn't matter. So it's equals to du and dt, right? So this is partial and this is d because, well, we know the V doesn't matter. We have the Cp is equals to this one, the dH over dt, similarly, because it's not a function of P. And we can have the dH over dt is a U plus PV, okay, U plus PV over dt, and is equal to this one, okay, U plus nRT over dt. So the Cv plus nR is equals to the Cp, right? So equals to the Cp. So for perfect gas, we were having the Cp minus the Cv is equal to Nr. Okay, so where this difference is coming from is because of the expansion work, right? So we already see that the expansion work is only equals to nRT, right? So in the previous examples. So this is the heat capacities, and we can have the molar heat capacities. So that is equal to the Cpm minus the Cvm is equal to R. So its understandings is for liquid and solid, the volume of the gas does not change with the P and T. So, well, because or doesn't change as much. So the delta U and delta H is almost constant, almost the same. Okay, Cp is almost the same as Cv because expansion works is almost negligible. Okay, unless you have extremely high pressure. Okay, unless you have extremely high pressure. Okay, let's do example questions here for the 1 mole of monoatomic gas. Okay, at the initial temperatures of this much. Okay, pressure of this much. The system undergo a following process. Okay, and I want you to calculate the Q, W, and delta U and delta H. Right. So the first process is simple. The system heat up. Okay, under constant pressures to this temperature. Okay, and then cool down to 25 degrees at constant volume. Okay, 1 mole of monoatomic gas. So you know what is the Cv and the Cp, right? And also the second process is the relevant expansions, reversible expansions at constant constant temperatures. Okay, so I want you guys to pause this videos, and for let's say okay, whatever the times, I think it's like 5 or 6 minutes maybe is enough, but just go ahead and do it. Okay, so let's check your answers. Okay, the first step is the constant pressure expansions. So we know because this is a constant pressure, so the Q, okay, is equals to the delta H, right? So the second step is constant volume. So then cool down to the constant volume. So this is a QV or delta U. We know these first steps of the delta H is equals to the N Cpm delta T, but basically this is 1 mole. So the Cp is very simple. So Cp delta T1, and this is a Cp Cv delta T2. Sorry, the second steps. So we know that the Q is equal to several Qs, right? So first step plus the second term. Okay, first step is this much. Second term is this much. Okay, it's equals to finally, okay, 9.91 kilojoules. For perfect gas, okay, the delta H and delta U are like not only related with the temperatures. So we know that. Okay, so the final initial temperatures are actually constant. Okay, they're actually the same. So the delta U and delta H would be equals to 0. Because the delta U and delta H is equal to 0, so I can calculate it. The W, okay, the work is equal to delta U minus Q is equals to this much. Okay, so it's just an easier way. You can follow that. You can calculate all the Q and all the W's and add together, so you're getting the same result. Okay. The second process, reversible expansions to certain numbers. Okay, reversible expansions because the temperature is isothermal, so it's constant. So delta U and delta H is all equals to 0. So that is simple. Okay, so this is not so if this is not a perfect gas, it's not going to be equal to 0. Okay, and for perfect gas, reversible expansions at constant pressures. So this is work is equal to minus nRT log. Okay, Vf over Vi, right? So Vf over Vi is because it's a perfect gas. It's equal to the Pi over Pf, right? So it's equals to this as well. So you can have this numbers. Okay, this numbers. Okay, around like minus 3.99 kilojoules. Okay, and delta U is equal to 0, and Q is equals to okay this numbers. This is using the first law of thermodynamics. Okay, very simple. Okay, so this is our check questions. Okay, So if you have time, like do this in-class exercise again. Okay, so like this question is relatively simple. So like if you have time, like really, but you need to practice this because like maybe in the test or in the assignment you're going to do that. Very simple. Okay, so how to do this? Okay, how to do this? Okay, like 2 mole of hydrogens initially at T1 is equal to 0 degrees Celsius, and temperature is reversible, expanded to 100 liters at constant pressures. Okay, again, ask you to calculate Q, W, and W. Right. So in this case, hydrogen CP is given. Okay, 29.1 joules per Kelvin per mole. Joules per mole per Kelvin. Okay. Usually, okay, for my convenience, okay, I would like to write this down, okay, as a diagram. I would like to write it down as a diagram. Okay. So go ahead, like do this in-class exercise, like if you have time. Okay. So what I do is I always put in here. This is write down all the initial steps. Okay, initial conditions. Okay, hydrogen 2 mole. Okay, temperature, give it to me. Okay, what is the pressures? Okay, give it to me. And then the volume. Okay, it doesn't say, but overall after it gives. It doesn't give me the temperature, but gives me the volume. Right? Because this is a perfect gas, can be considered. So I can calculate the V and T is actually given, right? So so we need to know the final temperatures because we want to know the U, right? So if we actually like because we know the initial temperatures, if I know the final temperatures, I know that there are U already. Okay, that will be very simple. And constant pressure irreversible expansions. Okay, this is actually going to give me some calculations results, right? So I could calculate what is the initial V1, and the temperatures can be calculated 610 Kelvin. So then I can calculate it the work, okay, the work and the heat. The heat, because I said that what we can do is using the I'm sorry, the delta U can be calculated as the CV delta T. Right, CV delta T, because this is perfect gas, and you can do this way as well. So work is equal to nRT delta T, right? So because this is a P is constant, okay, so this is equal to this. It's going to give me the numbers of minus 5.59 kilojoules, and the heat is what the delta H is equal to the NCP and delta T, right? So this just going to give me this one. Okay. This is actually the same. All right, so hopefully like these calculations like it is clear to you, okay? Because we're going to go over this kind of calculations over and over again, and some of the things equations can be always used. Some of the equations is used as a condition. Okay, for example, like when you can use the delta U is equals to the CV delta T. Okay, sometimes like a CP delta T is equal to H. So when you can use that, okay, just think about that. Okay, so that's all. Like we're going to talk about the thermal chemistries. So you actually like learned this in the general chemistry already, but like we're going to review it really quickly. So when you actually have a chemical reactions, right? So when you have a chemical reactions, the temperatures of the product and the system is always changing because it actually involves the breaking of the chemical or forming of the chemical bond. So that would cause the releasing or absorb the heat, right? However, like when we're actually having this, right? So we have the equations: QP is equal to delta H, and QV is equal to delta U. So remember, when we actually derive these equations, we don't consider the chemical reactions, right? So that means if you have a chemical reactions, all of these would hold, right? So would hold as well. So, like doesn't matters. So that's why when we actually say, okay, expansion of the perfect gas or compressing of perfect gas, we're not having specifically of any chemical reaction there because it doesn't matters. Okay, it doesn't matters. Okay, So these are some of the exothermic chemical reaction. Combustion is one. Okay, and here if you mix like acid and base, you actually generate temperatures as well. Okay, increase in the temperature as well. So this is one of the experiments. Okay, one of the experiments like people can do. Okay, so this is actually combining the acid and base. You actually generate heat. Okay, so if we actually in the class, like I usually do this in this experiment, but like this time I'm not going to do that. Okay, and so just showing this experiment. Okay, this is what I did in my lab. It's actually the hydrogen and the oxygen, they actually combine into the waters. Okay, the delta H or standard entropy of the combustion is minus 188 kilojoules per mole. Okay, this would be reactions. Okay, so first thing I would put in some mixed hydrogen and oxygens into this gas bubbles or into this bubble water. Okay. And then like I can ignite it. Actually, like in the lab, this is extremely loud. Like of course, like the cameras cannot catch the sound. Okay, the sound is extremely loud. Okay. Anyway, in here, I want to ask this question: what is the delta H? Particularly in the process of ignition. And what is the heat in here? Okay, in the process of ignition. So because it actually happens very quick, right? So after a while, it's like they actually dissipated heat. Okay. In here, we set the QP is equals to the delta H, and how much heat was really generated in here. Just think about that. Because this chemical reaction happens so quickly, right? So like in microsecond or so, you're already complete. And everything expanded and becomes a hydrogen, not really the water, but actually the gas, the vapor. Because of that, the heat have no time to come out, right? So this is actually a adiabatic process, right? Because the heat doesn't have a time to escape out of the systems. So as a result, the heat, the QP, because this is still a constant pressure process, the QP is equal to 0, or the delta H of the process we just say is actually equals to 0. Okay? So then you say, okay, what happened? Okay, what happened in here? This delta H is equals to minus 188 kilojoules. So why you said this is delta H is actually equals to 0? Because the condition is different, right? So here we're writing this conditions. That means this delta H is a condition where hydrogen, okay, whatever temperatures, it could be like room temperatures, react with a room temperature of the oxygen, becomes the room temperature of the water as a liquid. If this process finished, I would have the delta H is equals to minus 188 kilojoules. But in our case, here, when I ignite these bubbles, it goes so quickly. So what I have is the hydrogen generated or combined with oxygen. I generate the water vapor of the high temperature and high pressure, right? So they actually generate a high temperature of the water vapor, and the temperatures is so high that essentially equivalent to absorb the heat from the whatever the room temperature of the water. So this would create a positive delta H, and that positive delta H just cancels with the delta H of the combustion reaction. So I would get, so like the next question is, okay, what is the temperatures of the of the water vapor, right? Okay, just let's see again. It goes extremely quick. All right. Let's review a little bit about the standard condition of the standard state. So this is related with this one, right? So when we actually said what is the delta H of the chemical reactions, it's actually referring to the standard condition of a chemical reaction, right? So it's a standard condition of the hydrogen react with the standard condition of the oxygen, getting a standard condition of a water, right? So standard condition is a pure substance at 1 bar pressure. So 1 bar is 10 to the power 5 Pascal. So it's almost equals to the 1 atmosphere, but it's actually slightly lower. Okay. The physical state needs to be stated. So it's a gas, liquid, and solid, whatever it is, it has to be written. And I have a standard state. It's 1 bar. Okay, whatever this one. Okay, hydrogen. Okay, like gas. Okay, 1 bar. Okay, CO2, 1 bar. And this is a calcium carbonate. Okay, and this that's a solid at 1 bar. Okay, it is a convenient to assume this is like okay, room temperature, unless it's other way standard. Okay, so actually it's not, like it could be different, right? So all the standard condition doesn't define the temperatures, but if it doesn't say anything, just we assume this is like 25 degrees Celsius. So the standard entropy of a formation of the element is considered as 0. Okay, this is by definition. For the element, the heat and formation is defined as the 0 kelvins or 0 kilojoules per mole. Okay, for standard conditions. Okay, this is by definitions, because again, in the general chemistry, sorry, you know that there is no real numbers. Okay, like defined numbers for the U. Like the internal energies as well as entropes, because it will always getting a delta H and delta U. Okay, and delta H and delta U is defined in this way. So like with standard formation entropies and the standard combustion entropies. So this is a definition of standard formation of the element itself. The most stable form of the element is called 0. For in this case. The carbon, it's going to be the graphite. Graphite is the most stable form of carbon, so their formation entropy is going to be equals to 0. But diamond is not the standard, the most stable form of carbon, so you have the formation entropies. Okay, so for a formation entropies, or for entropy of chemical reactions, for example, I have the methane react with oxygen, getting the CO2 and water. I have this one. So this forms, so okay, this bar means it's a standard condition. Okay, delta H bar, okay, over here is equals to the minus 890 kilojoules per mole. Okay, so delta H, this means all is actually at the standard. So in here, what it actually saying? Okay, what is this chemical reaction really say here? So it says, okay, here, this is a standard condition. This is a standard condition. This is standard condition. This is standard condition. I have a standard condition of the methane react with a standard condition of the oxygen, getting a standard condition of CO2 and a standard condition of water. So standard condition means it's a pure substance. Okay, so pure substance of here, methane, react with a pure oxygen, getting the pure CO2 and the pure water. This is not a real chemical reaction. Okay, in real case, we have the mixture of methane with oxygen, getting a mixture of the CO2 with the water, right? So although we are writing these forms, this is not a physical reality. Okay, this is actually leading to why this chemical getting is a chemical equilibrium, because this is a mixture instead of a pure substance. Okay, so we can consider a model chemical reactions. Okay, model chemical reactions is 2 mole of A plus B becomes 3 mole of C plus D, and we can define a molar entropies of that if we can define, right? So we have initial state, we're getting the final state. if we ignore the interactions between these two. Okay. So the final one, we have the delta H, okay, reactions here is equals to the final minus the initial, because the product versus the reactant. So this is again not the real, because we don't have the pure substance. It's always the mixtures. But because this one is already a pure minus becomes a pure, so this is like mathematically correct. Okay, V is a stoichiometric coefficient in here, and we know all of these numbers. If we have all of these numbers, okay, we can calculate all any chemical reactions delta H bar, and this delta H later on can be translated into the heat. Okay, and this is the tables. Okay, thermodynamic data for elements and inorganic compound at room temperatures. Okay, we have the formation entropy. Formation gives free energies, and this is like a CP. Okay, like heat capacity. So, okay, this is all listed in the book. With this, we'll be able to calculate what is the reaction enthalpies. Here, this is the number we want, but here we don't have these numbers because this is a formation. This is delta formation of something, right? So delta G formation of something. So we don't have the H of the absolute numbers. So in order to get that, we will need to use the Heat's law. Okay, Heat's law, again, it's very simple. It's actually a function of the state function, or is a result of the state function, because we know the H or U, they're all state functions. That means it doesn't really depending on which route you're actually taken. If you have A and B directly reacted into the C and D, it will be the equivalent to goes through an intermediate. Okay. Intermediate, again, delta H1, and intermediate becomes like delta H2. So H1 plus H2 is equals to the this one, right? So it's equals to the whole difference. Okay, the total, the one-step reaction. All right. So this is if I have a chemical reaction go through here. So this what allows me to use this formation enthalpy to replace this real enthalpy, right? Because the formation enthalpy is essentially becomes I could using this. Okay, combine a root. It's starting with an element and gets into some kind of compound, and this compound becomes another compound, and I can calculate it overall. Okay, without using this. Okay, the real H, I can use a formation enthalpy. Okay, so what else? Like if this is not through a chemical intermediate, it's actually through a different temperature. If this is through a different temperatures, this is called the Kirchhoff law. So if I know the delta H of a room temperature, and I want to know what is delta H of another temperature, higher temperatures or lower temperatures. So the difference is really the delta H, okay, whatever temperatures bar is equals to a delta H of this temperatures bar plus, okay, delta Cp and delta T. Okay, delta Cp. And delta Cp is a heat capacitance difference is equals to the product minus the reactant. Okay, this delta means always final minus initial, and delta T is final minus initial. Okay, not final. Like this is like T minus whatever this like the room temperature, T minus 298 Kelvin. Okay, this is a temperature difference. Okay, the entropy of each substance increased basically by Cp delta T at a constant P, and then I'm going to get higher temperatures. 1. Okay. So before this class finish, okay, like I want you to do one more in-class exercise. Okay, very simple, coming from the book. Okay, the enzyme of glutamines, the synthesis mediates the synthesis of amino acid. Glutamines forms from the amino acid, obviously glutamate and ammonia ions. So this chemical reactions is glutamate becomes a glutamines, and have a delta H R, so R means reaction. Okay, delta HR reaction bar is equal to these numbers. And this process is endothermic and require energy extracted from the oxidation of the biological fuels and stored in the ATPs. And I want you to calculate the value of the enthalpy of the reaction at 60 degrees Celsius, and with the following reactions conditions. Okay, we have the CP and CP and CP, and also the CP here. Okay, extremely simple. Just go there and do the calculations. Because we're going this relatively quick because I assume you already learned this in the general chemistry. Okay. All right, so let's check our answers. Okay. Step 1, we'll actually calculate the delta R of the CP is equal to this number. Okay, whatever this product and the reactant. So we put all the numbers in there because all these stoichiometric ratio is 1. So you can see over here. So this is 1, 1, 1, 1, right? So this is all. So you can just like directly add it. Okay, the product minus the reactant, I'm getting these numbers. Okay, so the delta CP is equal to this one. And step 2, I can calculate the enthalpy of the reactions. So delta T is equals to, because 60 minus the 25 is equals to the 35 Kelvin. So I have this high temperature, 60 degrees Celsius, is equals to whatever the numbers. Okay, the delta H as a room temperature plus the delta CP and the delta T is equal to these numbers. All right, so I think that is all I want to talk at this time. So we can continue next, and hopefully you have a good Chinese New Year's.